Hello. Today I'll be speaking about new developments in the theory of nuclear fission using an approach called TDSLDA, which is an extension of time-dependent density functional theory to superfluid systems, and it was introduced to the fission problem about 10 years ago. So one of the first results that was achieved using TDSLDA was full separation between the fission fragments, starting from the outer saddle point, which corresponds to this deformation here. Whoops, my movie has a mind of its own. We go. So we can see we have a nuclear shape which starts in a deformed configuration, and then over time it separates. And we didn't provide a lot of additional excitation energy apart from what was required to put it into that deformed state. Another result from this approach was that the approximation of adiabatic motion was strongly violated. So let me explain what this means using this figure. On the horizontal axis, we have the quadrupole deformation of the nucleus, which can be thought of as the elongation. And what this surface represents here is it represents the ground state of the nucleus constrained to have a specific deformation. So this is the nuclear ground state, and as it deforms, the deformed ground state follows this trajectory. And the approximation of adiabatic motion is that as the nucleus evolves in shape, it will always um, be in its deformed ground state, and then as it sort of descends on this potential energy surface, it will acquire kinetic energy. If I draw your attention to this red curve here, we see an actual TDSLDA trajectory where something different happens. So this black line is supposed to indicate just the starting energy, where at first there's no flow energy because we're subtracting the kinetic energy. And then we see as time evolves, this red curve drops below the black curve, and the difference between these two things is the flow energy or the kinetic energy as a function of time. And we see that if the adiabatic approximation were to hold, then this red curve would in fact fall much closer to this potential energy surface, but in fact that is not what we see. And instead of the energy being transformed from potential energy into kinetic energy, it's transformed into internal excitation energy, and the nucleus heats up. So the fragments emerge from fission hot and with substantial intrinsic spins. So what we have on the left here is we have the distance between the fragments measured in units of femtometers here, and then we have the octopole moment on the vertical axis here. And we should think of fission as happening somewhere around 16 or 17, represented by this frame here. We see that we have a substantial octopole deformation. These curves represent light fragments from various simulations. These curves represent heavy fragments. There's a substantial octopole deformation, and then after fission, this deformation eventually relaxes. The energy that is in that deformation is, as the shape relaxes, it gets converted into even more internal excitation energy of the fragments, causing them to heat up further. We also have information on the fragment intrinsic spins. So on the horizontal axis of this figure, we have the total intrinsic spin of the fragment in units of h bar. On the vertical axis, we have k, which is the projection of that spin along the fission axis. We have the light fragment here. We have the heavy fragment here. We see that for the heavy fragment, there's a rather large spread, which is peaked around somewhere around 10 h bar for the intrinsic spin for the light fragment and something like 5 or 6 for the heavy fragment. And in fact, more than half the time, this k is non-zero, which conflicts with another leading phenomenological approach, at least at the time this study was released. Another prediction coming out of TDSLDA pertains to the so-called scission neutrons, which is a contentious topic dating back basically to the founding of fission itself. But here we see a time series of slice through the neutron density presented in a log scale. We see that a cloud of neutron matter is released according to our simulations, first with a ring-shaped distribution of neutron matter perpendicular to the fission axis, and then with a slight delay, an emission of neutron matter along the fission axis. And we can characterize the number of scission neutrons as well as the distribution of energy, and there's some hope that maybe between these two things, one might be able to measure these scission neutrons. Those discussions are ongoing. So here I just have a typical shape evolution for asymmetric fission of even nuclei. Here we have the quadrupole, here we have the octopole moments. We see that they get funneled into this valley here. In a recent study, we looked at odd nuclei and the fission of odd nuclei, so odd mass and odd, as well as symmetric nuclei. And we see that under some circumstances, the shape evolution in Q2, Q3, quadrupole, octopole, can be highly complex. Same with symmetric fission. Just to conclude, these fission calculations are also pushing modern supercomputers to the limit. So in particular for the Fission neutron study that I'm showing here, we used the Summit supercomputer in 2022. We had to use the entire machine to run this simulation. It ran for 15 hours straight, simultaneously using 27,000 GPUs and producing approximately 88 terabytes of new data per time step. So really enormous simulations in order to perform these TDSLDA calculations. And with that, thank you for listening.